What are the chances of two stars simultaneously becoming visible to the naked eye, two powerful earthquakes striking Venezuelan ground, and the enigmatic interstellar visitor Oumuamua being buffeted by a solar tempest, all within a 72-hour span? Were this a fictional screenplay, creators would deem it implausible due to its sheer improbability. Yet, this is our reality, and reality has just orchestrated an unprecedented celestial display. Following these occurrences, even the most skeptical minds might question whether we are witnessing more than mere chance. Tonight, we will meticulously analyze each event, explore the scientific underpinnings of stellar outbursts and terrestrial tremors, and then delve into the intriguing intersection of coincidence and pattern recognition. Remain with us until the conclusion, for our findings concerning December 2025 may fundamentally alter our understanding of celestial phenomena. Part 1. An extraordinary sequence of events. Two stars erupt, two significant earthquakes rend the earth in Venezuela, and an object from beyond our solar system encounters a coronal mass ejection. All within days of one another in late December 2025. If you're sensing a message from the cosmos, you're not alone. Let's precisely map this confluence of cosmic occurrences. On December 23rd, astronomers identified V1935 Centauri, a nova in the southern constellation Centaurus that intensified to a magnitude of 5.8, rendering it visible without optical aid. Within days, another stellar detonation announced itself, V7994 Sagittari, flaring in the constellation Sagittarius with a magnitude of 6.2. Two stars, both suddenly observable to anyone looking skyward. Meanwhile, thousands of miles from the nearest astronomical observatory, the Earth itself made headlines. At 22:21 UTC on December 24th, a magnitude 6.2 earthquake struck 24 kilometers east, northeast of El Mene Grande in Venezuela's Zulia state. The seismic event, originating a mere 7.8 kilometers below the surface, sent tremors across both Venezuela and Colombia. But nature's activity continued. Hours later, at 0351 UTC on December 25th, a second quake, magnitude 6.3, originated in the same vicinity, this time from a depth of 14 kilometers. Twin stars, twin earthquakes, and overhead, imperceptible to the unaided eye but tracked by satellites, another phenomenon was unfolding. Solar weather forecasters at NOAA's Space Weather Prediction Center were monitoring coronal mass ejections, colossal clouds of magnetized plasma ejected from the sun at speeds exceeding 1 million miles per hour. Their predictive models indicated these solar storms were intersecting with something extraordinary. 2I Borisov, the second confirmed interstellar visitor to our solar system. The timing of these events is remarkably synchronized. The nova discoveries and Venezuelan earthquakes occurred around December 23rd through the 25th. CME forecast models predicted peak activity within the same time frame. And 2I Borisov, discovered just 2 months prior by the Atlas survey, was traversing the inner solar system during what is considered a highly active period of solar cycle 25. The spatial scale of these events defies conventional comprehension. The novae erupted in Centaurus and Sagittarius, constellations predominantly viewed from Earth's southern hemisphere, their light having traversed millennia to reach us precisely during this significant week. The earthquakes occurred near El Mene Grande in northwestern Venezuela, a geologically intricate area where the Caribbean and South American tectonic plates interact. The coronal mass ejection propagated through the inner heliosphere, a region vastly larger than Jupiter's orbit. And 2I Borisov was crossing the ecliptic plane, the imaginary disk where most planetary motion occurs, navigating between Mars and the Sun. We are not asserting a direct causal link, as that would be premature, perhaps even reckless. Instead, we are documenting this convergence and preparing to compare established scientific explanations with more speculative hypotheses. The U.S. Geological Survey finds no established connection between space weather and seismic activity. Solar physicists explain coronal mass ejections as routine solar phenomena. Stellar astronomers view novae as predictable, albeit unpredictable, outcomes of binary star evolution. However, what makes this week truly exceptional in recent astronomical history is that 2I Borisov represents only the second confirmed interstellar object ever detected, following Oumuamua in 2017. More significantly, this is the first instance where an interstellar visitor might be observed interacting with intense solar weather near a solar maximum. We have observed the effects of CMEs on solar system comets. In 2007, the European Space Agency's stereo satellites captured a coronal mass ejection, severing the ion tail of comet Enki, a stark demonstration of violent space weather interactions. The implications for the coming months extend beyond academic interest. 2I Borisov is projected for a flyby of Mars on October 3rd, passing within approximately 28 million kilometers of the red planet. Mars orbiters, including ESA's ExoMars and NASA's Mars Reconnaissance Orbiter, are poised for opportunistic observations that could reveal unprecedented details of the interstellar visitor's nucleus and coma. Specifically, on October 29th, 2I Borisov will reach perihelion, its closest approach to our Sun at 1.36 astronomical units, still beyond Earth's orbit, but close enough for ground-based telescopes to study its composition and behavior in real time. The viewing conditions will become even more favorable by December 19th, when 2I Borisov makes its closest approach to Earth at 1.8 astronomical units. For perspective, this is closer than Mars at its most distant, offering extended observation opportunities for both professional observatories and amateur astronomers with modest equipment. This convergence occurs during a period when space weather typically intensifies. The autumnal equinox triggers what space physicists term the Russell-McFarlane effect, a geometric anomaly in Earth's magnetic field orientation that amplifies geomagnetic coupling with solar wind disturbances. December through November historically yield some of the year's most spectacular auroral displays and significant space weather impacts on technology. We pledge to provide both clear scientific explanations and bold hypothetical scenarios, meticulously labeling each. You deserve to distinguish between observational confirmation, scientific speculation, and outright imagination. The data is paramount, as is the sense of wonder. And sometimes the most honest scientific statement is, "We do not yet know, but we are observing." Consider this question as we delve deeper. If coronal mass ejections can strip the tails from comets that have orbited our Sun for millennia, what might they do to an object that has spent millions of years traveling between stars, carrying ice and dust formed in an entirely different stellar system? We are on the verge of finding out. Next, we will examine those sudden stellar eruptions, the twin novae that illuminated the southern skies just as Earth's crust began to tremble. Part 2. The two novae, sudden southern sky eruptions. In the pre-dawn hours of December 23, 2025, amateur astronomer John Seach was engaged in his decades-long pursuit, scanning the southern skies from his observatory in Culburra Beach, New South Wales, searching for stellar explosions. What he detected that morning would soon capture the attention of gamma-ray satellites and X-ray telescopes across the solar system. V1935 Centauri announced its presence not with fanfare, but with photons. Seach's initial observation revealed a star previously not bright enough to warrant notice, located in the constellation Centaurus at magnitude 5.8, just bright enough for keen observers in dark locations to discern without binoculars. But this was no ordinary brightening. Within hours of Seach's discovery report reaching the Central Bureau for Astronomical Telegrams, space-based observatories began registering something extraordinary. NASA's Fermi Gamma Ray Space Telescope triggered on high-energy photons emanating from the nova's direction. The Swift Observatory, designed to detect gamma-ray bursts, reoriented its X-ray telescope toward Centaurus, commencing the recording of hard X-ray emissions, indicative of violent particle acceleration within the nova's expanding shock wave. These were not merely aesthetic displays for backyard stargazers. They were evidence of physics operating at extreme levels. Electrons and protons accelerated to near light speeds, magnetic fields contorted into complex configurations, and temperatures soaring into the millions of degrees. Yet, V1935 Centauri was not finished making news. Merely days later, the cosmos struck again. V7994 Sagittari erupted in the adjacent constellation, Sagittarius, reaching a magnitude of 6.2 upon its discovery. Two stellar explosions, both attributed to the same observer, both bright enough for small telescopes or binoculars, both occurring within the same remarkable week. This pair surprised professional astronomers because, while novae are not exceptionally rare, with approximately 10 to 12 occurring in our galaxy annually, two reaching near-naked-eye visibility within days is genuinely uncommon. The last instance of two bright novae being observed simultaneously was in the summer of 2023, and prior to that, one would need to search back several years for comparable events. The physics underlying these eruptions tells a story of stellar interactions unfolding over cosmic timescales. Each nova originates with a white dwarf, the dense, hot remnant core of a star roughly the size of Earth, but possessing the mass of our Sun. This stellar remnant orbits a companion star, gradually siphoning hydrogen from its outer atmosphere. Over years, centuries, or millennia, gas accumulates on the white dwarf's surface, becoming denser and hotter under immense gravitational compression. Eventually, temperature and pressure reach a critical threshold, initiating a runaway thermonuclear fusion of the accumulated hydrogen, not the controlled burning that sustains living stars, but an explosive conflagration that can amplify the binary system's brightness by factors of 10,000 or more. The explosion does not obliterate the white dwarf. Instead, it expels the surface layer, returning the system to its patient process of accumulation. Some novae recur on predictable schedules, erupting every few decades, while others may experience thousands of years between outbursts. V1935 Centauri's gamma ray and hard X-ray signatures reveal the nova's most violent aspects. When the thermonuclear explosion propels material outward at speeds of thousands of kilometers per second, it generates shock waves that accelerate particles to prodigious energies. These relativistic particles interact with magnetic fields and surrounding matter, producing the high-energy photons detected by Fermi and Swift. This is the same physics observed in supernova remnants and active galactic nuclei, cosmic particle accelerators that transform ordinary matter into high-energy radiation. For observers in Earth's southern hemisphere, both novae occupy prime viewing positions. V1935 Centauri is located well south of the celestial equator, making it a challenging target for northern observers who must await its ascent above their southern horizon. V7994 Sagittari, situated in the constellation Sagittarius, presents a similarly southern viewing geometry, appearing low in the south for observers at mid-northern latitudes, but high in the sky for anyone south of the equator. The discovery process itself underscores the collaborative nature of contemporary transient astronomy. Seach's initial observations, reported through the International Astronomical Union's Central Bureau, triggered a cascade of follow-up investigations. Circular number 5611 confirmed the detection of V1935 Centauri, while circular number 5612 documented V7994 Sagittari. Within days, observatories worldwide were acquiring photometry, precise brightness measurements, and spectroscopy that revealed the characteristic emission lines of hydrogen, helium, and heavier elements in the expanding nova shells. Amateur astronomers play a vital role in nova science through organizations like the American Association of Variable Star Observers. Their nightly monitoring provides the temporal resolution necessary to observe the evolution of nova light curves. The complex patterns of brightening, plateau phases, and gradual decline that offer clues about the explosion physics and the properties of the binary systems. Professional telescopes cannot continuously monitor every nova, but dedicated amateurs can track brightness changes night after night, contributing data that enhances our understanding of these stellar explosions. The naming convention can sometimes confuse newcomers to astronomy. V1935 Centauri received its designation as the 1935th variable star, officially named in the constellation Centaurus, while V7994 Sagittari became the 7994th in Sagittarius. These permanent names supersede the temporary designations assigned at discovery, which can occasionally lead to apparent timeline discrepancies when later discovered objects receive earlier numerical designations due to administrative processing delays. Both novae are expected to fade over the ensuing weeks and months, following the typical nova decline, which can span months to years. However, their evolution may hold surprises. Some novae develop dust formation episodes weeks after eruption, temporarily dimming as newly formed dust grains absorb and scatter the nova's light. Others exhibit complex, multi-peaked light curves as different physical processes dominate at various stages. The question that space weather enthusiasts invariably ponder is whether these stellar explosions, occurring concurrently with significant geomagnetic activity, represent more than mere coincidence. The prevailing astronomical consensus is clear. Novae in neighboring constellations, situated thousands of light years from Earth, pose no direct threat to our planet and exert no measurable influence on terrestrial phenomena. The energy from these explosions, while immense by human standards, dissipates across the vast expanse of interstellar space, reaching Earth as a subtle increase in photons, beautiful to behold, harmless to experience. Yet the timing feels remarkable. Twin stellar eruptions during a week marked by twin earthquakes, with an interstellar visitor traversing a region of active solar weather. Perhaps the most honest response is to acknowledge both the science and the synchronicity, to appreciate the physics while remaining open to the possibility that our universe occasionally arranges itself in ways that elevate coincidence towards something akin to poetry. Meanwhile, thousands of miles from any observatory capable of observing these celestial fireworks, the solid Earth beneath Venezuela was about to demonstrate that explosions were not confined to distant suns. Part 3. The Venezuelan Earthquakes. At precisely 22 hours, 21 minutes, and 55 seconds, Coordinated Universal Time on December 24th, the Earth's crust beneath Venezuela's Zulia state released energy equivalent to several nuclear weapons. The magnitude 6.2 earthquake struck 24 kilometers northeast of El Mene Grande, originating from a relatively shallow depth of 7.8 kilometers, close enough to the surface to shake buildings across two nations. The seismic waves propagated outward at approximately 6 kilometers per second through the rock, reaching populated areas within seconds of the rupture. From Maracaibo to Caracas, from Colombian border towns to Caribbean coastal cities, millions of people felt the ground tremble beneath their feet. Social media platforms exploded with videos of swaying chandeliers, rattling windows, and residents evacuating buildings as emergency protocols were enacted across the region. But the Earth was not yet finished. Merely 5.5 hours later, at 03 hours, 51 minutes and 39 seconds UTC on December 25th, a second major rupture occurred in virtually the same location. This time, the magnitude 6.3 earthquake originated from a depth of 14 kilometers, deeper than its predecessor, but still shallow enough to generate intense surface shaking. The epicenter was located approximately 27 to 28 kilometers east-northeast of El Mene Grande, overlapping the rupture zone of the initial event. To comprehend the significance of these twin quakes, we must understand the logarithmic nature of earthquake magnitude scales. A magnitude 6.3 earthquake releases approximately twice the energy of a magnitude 6.2 event. Combined, these two ruptures released energy equivalent to a single magnitude 6.4 to 6.5 earthquake, a significant release even by global standards. The December 24th and 25th events represented the most substantial seismic activity in the region since the magnitude 7.8 Kamchatka earthquake on December 18th, placing Venezuela's twin quakes among the most notable global seismic events of late December 2025. The aftershock sequence provided its own drama. A magnitude 5.8 earthquake struck the same region later on December 25th UTC, following the typical decay pattern that seismologists anticipate after major ruptures. While 5.8 might sound modest compared to the main shocks, it is still significant enough to cause additional damage and maintain anxiety levels among regional populations already stressed by two major events. Regional tectonics explain the occurrence of such powerful earthquakes in this area. The Maracaibo Basin lies within a complex zone where the Caribbean plate grinds against the South American plate, creating a network of fault systems, including the Bocano Fault System and the Oca-Santa Marta fault trends. These geological boundaries have been accumulating stress for years, decades, or centuries, storing energy that is eventually released through sudden slip events, earthquakes. The difference in depth between the two main events, 7.8 kilometers versus 14 kilometers, significantly impacts ground shaking intensity. Shallow earthquakes typically produce stronger surface acceleration than deeper events of the same magnitude because seismic waves have less opportunity to spread out and attenuate during their journey to the surface. The shallow depth of the December 24th event likely contributed to the widespread reports of strong shaking across both Venezuela and Colombia. Different seismological agencies reported slightly varying magnitudes for these events, reflecting the complexities of earthquake measurement. The United States Geological Survey initially reported the first earthquake at magnitude 6.2, while the European Mediterranean Seismological Center and other international monitoring networks provided measurements ranging from 6.1 to 6.3. These differences arise from various factors: distinct measurement methodologies, updates as additional seismic station data becomes available, and distinctions between moment magnitude, surface wave magnitude, and body wave magnitude calculations. The human impact of these earthquakes extended far beyond seismological statistics. Evacuation orders affected thousands of residents, particularly in multi-story buildings that experienced prolonged swaying during the events. Emergency response teams mobilized across the region, conducting damage assessments and ensuring that critical infrastructure, hospitals, bridges, power plants, remained operational. While initial reports suggested relatively limited structural damage given the earthquake's magnitudes, assessment teams continued their work for days following the events, documenting both visible damage and potential long-term structural weakening. Historically, this region has experienced significant seismic activity. The complex tectonics around Lake Maracaibo and the broader Caribbean-South American plate boundary generate regular earthquake sequences. Although seismic upheavals of such magnitude are infrequent, geological evidence indicates that major fault breaks in this geographical area can, on occasion, precipitate further seismic activity along adjacent fault lines. This phenomenon is known as stress transfer, which occurs when one earthquake alters the stress distribution on neighboring fault systems. The timing of these events sparked curiosity among both professional geoscientists and the general public. Could more significant seismic events follow? The statistical response to this question is complex. Sequences of aftershocks are anticipated and are considered a normal occurrence, with the most substantial aftershocks typically happening within days to weeks of the primary tremor. However, geoscientists are unable to reliably forecast whether an even larger earthquake might strike in the same vicinity in the near future. The discipline of earthquake prediction continues to be an elusive pursuit, despite decades of research focused on precursory indicators, stress accumulation patterns, and statistical forecasting methodologies. Global monitoring networks diligently tracked every aftershock, gradually constructing a comprehensive understanding of how the fault system was reacting to the stress shifts induced by the two substantial ruptures. The Global Centroid Moment Tensor Database commenced the processing of detailed analyses concerning the fault orientations, slip vectors, and rupture mechanisms for both seismic events. This information proved invaluable to geoscientists in determining which fault segments had actually moved and how the stress field had been altered across the broader region. For the inhabitants of Zulia State and surrounding territories, these twin earthquakes served as a stark and sobering reminder of their region's inherent geological vulnerabilities. Building regulations, emergency preparedness measures, and community response frameworks all undergo significant testing during such catastrophic occurrences. The comparatively moderate level of damage reported, considering the magnitude of the earthquakes, likely reflects a combination of fortunate timing. The events transpired during hours when many individuals were at home rather than in potentially perilous workplaces, and ongoing enhancements in construction standards and emergency response capabilities. The broader inquiry that emerged from these seismic incidents pertains to their timing in relation to other notable occurrences during that same extraordinary week. Geoscientists maintain that there is no established physical mechanism that demonstrably links solar activity, space weather phenomena, or celestial events to the occurrence of earthquakes. The official stance of the United States Geological Survey underscores that any correlations observed between space weather and seismic activity remain unsubstantiated, notwithstanding periodic assertions found in both scientific literature and popular media. Nevertheless, the human mind has an inherent inclination to seek patterns, particularly when dramatic events coincide within a concentrated time frame. Twin novae, twin earthquakes, heightened solar activity, and an interstellar interloper traversing the inner solar system. The convergence feels momentous, even if the underlying causal links remain obscure. Perhaps the most scientifically sound approach involves meticulously documenting the sequence of events, understanding each phenomenon independently, and maintaining an openness to discovering potential connections while steadfastly resisting the temptation to infer causation from mere correlation. As aftershocks continued to reverberate through Venezuela's collective consciousness, the sun was concurrently preparing to illustrate that Earth's immediate cosmic environment could be just as dynamic as its solid terrestrial surface. This marks the beginning of Part 4, the Sun Fires. 93 million miles above Venezuela's trembling ground, our star was orchestrating its own spectacular explosive symphony. During the very same days that stellar outbursts illuminated the southern heavens and earthquakes rent the South American bedrock, the sun unleashed coronal mass ejections, immense clouds of magnetized plasma, weighing billions of tons, which would cross the path of an entity unprecedented in human experience, an interstellar visitor. Coronal mass ejections represent some of the most potent events within our solar system. These dramatic eruptions originate in the sun's corona, where magnetic field lines become increasingly twisted, entangled, and eventually snap, much like overstretched elastic bands. When magnetic reconnection occurs, it unleashes energy equivalent to that of billions of hydrogen bombs, accelerating plasma to velocities ranging from 250 to 3,000 kilometers per second, fast enough to traverse the distance between the Earth and the Sun in 1 to 4 days. NASA's Space Weather Prediction Center diligently monitors these solar storms, utilizing the WSAE NLI model, a sophisticated computational simulation designed to map the propagation of coronal mass ejections through the heliosphere. This model takes into account solar wind speed, density, and magnetic field orientation to forecast the timing and locations at which these plasma clouds will intersect with spacecraft, planets, and other celestial bodies in their trajectory. Throughout late December of the year 2025, Enlil forecasts indicated heightened activity, with multiple coronal mass ejection events threading their way through the inner solar system during the same period that brought us the twin novae and the twin earthquakes. However, this is where the narrative takes a uniquely historical turn. For the very first time in recorded human history, one of these solar storms was on a direct collision course with an object originating from another star system. 3I 2023 P1, also known as Oumuamua, discovered merely 2 months prior by the Asteroid Terrestrial Impact Last Alert System, was traversing the inner heliosphere amid some of the most active conditions of solar cycle 25. This interstellar interloper, following a retrograde orbit inclined at approximately 175 degrees to the ecliptic plane, was crossing the same expanse of space that our Earth inhabits, a prime region for encounters with space weather phenomena. We possess documented instances of what transpires when coronal mass ejections collide with comets. Such interactions are not subtle conjectures. They are substantiated physical events captured by spacecraft cameras and meticulously analyzed in peer-reviewed scientific publications. In 2007, the European Space Agency's stereo satellites recorded a coronal mass ejection completely severing the ion tail of Comet 17P Holmes. This disconnection event, which persisted for several hours, starkly demonstrated the forceful reality of magnetic reconnection occurring between solar plasma and cometary material. Comet tails are formed through two distinct processes, each responding differently to solar influences. Dust tails curve gracefully away from the sun, propelled by radiation pressure, the gentle yet persistent force exerted by sunlight striking microscopic particles. Ion tails, in contrast, stream directly away from our star, guided by magnetic field lines embedded within the solar wind. When a coronal mass ejection disrupts these magnetic connections, ion tails can detach entirely, drift away from the comet, and eventually dissipate, while new tails subsequently form from fresh ejected material. The assertion that 3I Atlas was grazed by a coronal mass ejection is predicated on trajectory analysis derived from computational models rather than direct visual observation. The Enlil forecast suggested that the paths of solar storms would intersect with the interstellar visitor's position during late December. However, we must maintain transparency regarding the inherent uncertainties. Space weather models excel at predicting broad trends, but often struggle with fine-grained details. Consequently, the interaction remains a projected inference rather than a definitively peer-reviewed detection. If the interaction did indeed occur, as the models suggest, we might anticipate several observable consequences. An increase in ionization could lead to a brightening of the interstellar visitor's coma, the diffuse envelope of gas and dust surrounding its nucleus. Alterations in the morphology of its ion tail might become apparent in telescopic imagery as disruptions in the magnetic fields influence the streaming of charged particles away from the object. Spectroscopic observations could reveal distinct chemical signatures as solar energy liberates specific molecules such as cyanide, CN, carbon monoxide, CO, and carbon dioxide, CO2, from the visitor's ancient ice. Amateur astronomers across the globe were strategically positioned to document any such changes. The extensive global network of comet observers, connected through online forums and astronomical organizations, maintains nightly visual records of noteworthy celestial objects. Their collected images, when compared over time, reveal subtle shifts in brightness, tail structure, and coma morphology that often elude detection by professional observatories preoccupied with other research objectives. The physical principles governing coronal mass ejection and comet interactions involve magnetic reconnection, the very same process that triggers solar flares and geomagnetic storms. When solar plasma, carrying tangled magnetic field lines, encounters a comet's ionosphere, these field lines can connect, disconnect, and reconnect, releasing energy that accelerates particles and generates observable phenomena. This represents elegant physics in action, the topology of magnetic fields transforming in real time, converting stored magnetic energy into the kinetic energy of charged particles. 3I Atlas represents more than simply another target for space weather interactions, as the third confirmed interstellar object detected, following Oumuamua in 2017 and Borisov in 2019. It carries material forged around a different star within a distinct stellar system, potentially billions of years ago. If solar storms can indeed influence its behavior, we are witnessing the inaugural documented instance of our Sun directly interacting with matter originating from another stellar neighborhood. The trajectory characteristics of the visitor make these interactions more probable than they were for preceding interstellar objects. Unlike Oumuamua, which transited the inner solar system rapidly and at a high inclination to the ecliptic plane, 3I Atlas follows a path that keeps it in close proximity to the ecliptic, the plane where solar activity tends to concentrate and where Earth experiences the majority of space weather effects. Solar Cycle 25 has provided an actively conducive backdrop for these interactions. This solar cycle, spanning from 2019 to 2030, reached its peak activity phase during the years 2024 and 2025, resulting in elevated sunspot counts, increased frequency of solar flares, and more numerous coronal mass ejections. The timing of this cycle means that 3I Atlas is encountering our Sun at its most tempestuous, subjected to space weather conditions that previous interstellar visitors did not experience. The observational verification of coronal mass ejection interactions necessitates meticulous analysis of changes in brightness, spectroscopic variations, and morphological evolution over time frames ranging from hours to days. Professional observatories and amateur astronomers worldwide maintained vigilant observation of 3I Atlas throughout late December. However, initial findings remained preliminary as the analytical process continued. The broader implications extend far beyond this single event. If we can document the ways in which our Sun influences interstellar material, we gain invaluable insights into similar processes occurring throughout the galaxy. Other star systems presumably eject their own coronal mass ejections, potentially impacting interstellar objects that traverse their respective vicinities. It is plausible that 3I Atlas carries within it the signatures of interactions with previous stellar systems it may have encountered during its multi-million-year journey through interstellar space. As December of the year 2025 drew to a close, the convergence of events, stellar explosions, terrestrial earthquakes, solar storms, and interstellar visitor interactions, created a temporal nexus that challenged comfortable assumptions regarding cosmic coincidences. Were we witnessing unrelated phenomena coincidentally aligning, or was a more systematic underlying force at play? The answer would begin to emerge as 3I Atlas continued its journey, culminating in a flyby of Mars on the 3rd of October, carrying with it whatever modifications might have been imposed by our Sun's coronal mass ejections upon this traveler from the stars. This leads us to Part 5, Weirdness Framed. Let us pause for a moment to reflect on what has been presented. Twin stellar explosions, visible to the unaided eye. twin earthquakes of magnitude 6 occurring within hours of each other, coronal mass ejections traversing the inner solar system, and an interstellar visitor crossing our cosmic neighborhood during a period of peak solar activity. An extraordinary amount of cosmic activity unfolding with remarkable rapidity, compressed into the final week of December in the year 2025. This is precisely where rigorous scientific inquiry intersects with humanity's innate capacity for pattern recognition. And this intersection is not always a comfortable one. Our brains have evolved to discern meaningful connections within complex environments. A rustle in the undergrowth that might signal the presence of a predator, a change in cloud formation that could indicate impending rain, or behavioral shifts that might suggest social threats or opportunities. This cognitive architecture serves us exceptionally well in numerous contexts, but it can also lead us to perceive significance in coincidental alignments. The scientific mainstream offers clear and unambiguous guidance regarding these events. The United States Geological Survey, for instance, explicitly states that no demonstrated physical mechanism links solar activity or space weather phenomena to earthquake occurrences. Decades of correlation studies have consistently failed to establish reliable predictive relationships between solar activity and seismic events. Professional seismologists emphasize that earthquake prediction remains an impossibility utilizing current scientific methodologies, irrespective of whether such predictions are based on terrestrial precursors or extraterrestrial influences. Similarly, stellar astronomers regard novae as predictable consequences of binary star evolution, occurring when white dwarf stars accumulate sufficient mass from their companion stars to trigger a thermonuclear runaway. The timing of nova eruptions is governed by stellar physics rather than terrestrial or solar system influences. V1935 Centauri and V7994 Sagittari represent typical, albeit visually spectacular, examples of processes that occur throughout our galaxy on a regular basis. Solar physicists study coronal mass ejections as natural outcomes of magnetic field evolution within the Sun's corona. These events transpire with greater frequency during periods of solar maximum, rendering late 2025 a statistically probable time for multiple coronal mass ejection occurrences. The interaction between solar storms and cometary material has been extensively documented, representing well-understood plasma physics rather than an exotic or novel phenomenon. Nevertheless, acknowledging the prevailing scientific perspectives does not necessitate the dismissal of the remarkable nature of this temporal clustering. Occasionally, the universe orchestrates events that approach a state of synchronicity, even if the underlying mechanisms remain prosaic. The fundamental question becomes, how do we simultaneously embrace rigorous skepticism and foster appropriate wonder? Our approach throughout this exploration will meticulously maintain distinct boundaries between different categories of claims. Observational facts, such as magnitude measurements, precise location coordinates, and spectroscopic detections, form the bedrock of our understanding. These represent what instruments have recorded, what satellites have detected, and what seismographs have measured. Building upon this foundation, we will construct layers of scientific interpretation grounded in established physics and thoroughly tested models. Beyond the realm of established science lies the domain of speculation, where we will venture with caution and explicit disclaimers. Speculative connections, potential relationships between solar activity and terrestrial phenomena, hypothetical influences of stellar events on solar system dynamics, and theoretical mechanisms linking cosmic and geological processes all merit exploration, provided we remain transparent about their status as hypotheses rather than established facts. For general audiences, the vocabulary of cosmic events requires clear definition. A nova is defined as a stellar explosion that dramatically brightens a binary star system by factors of thousands or millions, caused by a thermonuclear runaway reaction on the surface of a white dwarf star. This differs fundamentally from a supernova, which results in the complete destruction of the exploding star. A coronal mass ejection comprises clouds of plasma weighing billions of tons, ejected from the Sun at speeds ranging from hundreds to thousands of kilometers per second. Perihelion denotes the point in an object's orbit when it is closest to the Sun. An astronomical unit, AU, is equivalent to the average distance between the Earth and the Sun, approximately 93 million miles or 150 million kilometers. Ion tails form when the solar wind strips electrons from gas molecules within a comet's coma, thereby creating charged particles that subsequently follow magnetic field lines directly away from the Sun. These tails can extend for millions of kilometers through space, providing a visible manifestation of the invisible magnetic processes operating between stars and smaller celestial bodies. What will follow in our investigation will involve a clear delineation between observed phenomena and imagined connections, all while maintaining a profound respect for both scientific rigor and inherent human curiosity. We will delve into the intricate physics of stellar explosions, earthquake ruptures, and solar storm interactions. We will meticulously track 3I Atlas through its flyby of Mars on the 3rd of October and its approach to perihelion on the 29th of October. We will explore legitimate scientific hypotheses concerning potential connections between cosmic and terrestrial phenomena, alongside explicitly labeled speculation regarding more extraordinary possibilities. The autumnal equinox season traditionally amplifies space weather effects due to the Russell-McFadden effect, a geometric coupling between Earth's magnetic field and solar wind conditions that frequently intensifies geomagnetic activity during the months of December and October. This seasonal enhancement provides an additional context for why late December might exhibit elevated space weather activity, independent of any purported connection to other events. 3I Atlas presents unique scientific opportunities precisely because it represents our third confirmed interstellar visitor and the first observed during a period of intense solar activity. The geometry of its trajectory, passing near the ecliptic plane where most solar system activity is concentrated, maximizes the probability of multi-mission observations and space weather interactions. Unlike Oumuamua, which departed rapidly before comprehensive study could be conducted, or Borisov, which remained relatively distant, 3I Atlas offers extended observation opportunities spanning several months. The implications for October and November extend beyond mere academic interest. Mars orbiter missions, including the European Space Agency's ExoMars Trace Gas Orbiter and NASA's Mars Reconnaissance Orbiter, have scheduled opportunistic observations during the October 3rd flyby, potentially yielding imagery of unprecedented resolution detailing the nucleus and coma structure of an interstellar visitor. Ground-based observatories worldwide continue to monitor changes in brightness, spectroscopic evolution, and morphological variations that could elucidate how solar weather impacts interstellar material. Regarding earthquake monitoring in Venezuela, aftershock sequences typically persist for weeks to months following major seismic ruptures. While seismologists cannot predict the occurrence of larger subsequent events, they maintain continuous surveillance of regional seismic activity and the evolution of stress fields. The complex tectonic interplay of the Caribbean-South American plate boundary ensures that this region will continue to generate earthquakes, although the precise timing of these events remains fundamentally unpredictable. Our commitment is to present multiple perspectives with unwavering honesty. Mainstream scientific explanations warrant primary attention due to their foundation in established physics and extensive observational corroboration. Speculative hypotheses deserve consideration, provided they are consistently and clearly distinguished from proven scientific principles. The inherent human impulse to discern meaning within apparent patterns warrants respect, even when scientific evidence does not support causal connections. Perhaps the most extraordinary aspect of this confluence of events lies in its timing. We are living in the first generation in human history capable of detecting interstellar visitors, monitoring global seismic activity in real time, observing stellar explosions across the entire electromagnetic spectrum, and tracking space weather phenomena throughout the solar system. Previous generations might have noted the appearance of bright novae and felt the tremors of earthquakes, but they would have been unable to connect these events to solar storms and interstellar visitors, as the technological capacity to detect such linkages did not exist. We shall meticulously separate what is observed from what is imagined, what is proven from what is possible, and what is likely from what is merely conceivable. So, how do stars explode without being completely obliterated? The answer reveals physical processes operating at scales that challenge human intuition. This leads us to Part 6, Anatomy of a Nova. Imagine a white dwarf star, a celestial body roughly the size of Earth, yet containing the mass of our entire Sun. Its surface gravity exerts immense pressure, compressing matter to densities approaching 1 million times that of water. Its surface temperatures hover around 50,000 degrees Fahrenheit. This stellar remnant is what remains after a sun-like star exhausts its nuclear fuel, sheds its outer layers, and collapses into a sphere of degenerate matter, where atoms exist in states unattainable under terrestrial conditions. Now, envision this cosmic furnace locked in a gravitational embrace with a normal star. Imagine a colossal crimson star, its outer envelope expanded enormously as it ages. The gravitational pull of a nearby white dwarf steadily siphons hydrogen from its companion's vast atmosphere, drawing gas across the interstellar void in spiraling streams, much like water descending a drain. This pilfered material accumulates on the white dwarf's surface, growing denser and hotter under immense gravitational pressure. For decades, even centuries or millennia, hydrogen builds up. The temperature and pressure steadily climb as more matter piles onto the white dwarf's surface. Unlike the controlled nuclear fusion occurring in the hearts of stars, this accumulation builds towards an explosive release. When the temperature reaches approximately 100 million degrees Kelvin, a thermonuclear cascade is initiated. The celestial detonation that birthed V1935 Centauri unfolded in mere seconds. This runaway fusion consumed the accumulated hydrogen layer in a conflagration that unleashed energy equivalent to our Sun's total output over a span of thousands of years. However, here lies the critical distinction from a supernova. The white dwarf itself endures. The explosion expels only the outermost layer of stolen material, leaving the underlying stellar remnant intact and primed to repeat the process. This is precisely why the potent energy signatures emanating from V1935 Centauri captured the attention of observatories across the globe. When NASA's Fermi Gamma Ray Space Telescope registered gamma rays originating from the nova's direction, it was capturing evidence of particles accelerated to near light speeds within the shock fronts of the explosion. The Swift Observatory's detection of hard X-rays revealed electrons whizzing through magnetic fields at prodigious energies, generating synchrotron radiation across the electromagnetic spectrum. These high-energy phenomena elevate novae from simple brightening events to cosmic particle accelerators. The expanding shell of ejected material, hurtling outward at speeds of several thousand kilometers per second, generates shock waves upon colliding with the tenuous gas scattered between stars. These shocks function akin to natural cyclotrons, employing magnetic field acceleration to propel protons and electrons to energies that would necessitate colossal terrestrial laboratories to achieve. The American Association of Variable Star Observers orchestrates the contributions of amateur astronomers to nova science through standardized photometry protocols. Visual observers estimate brightness by comparing the nova to stars of known luminosity, while CCD cameras provide precise magnitude measurements that delineate subtle fluctuations in the nova's light curve. These observations, furnished by hundreds of amateur astronomers worldwide, offer the temporal resolution that professional observatories, tasked with monitoring numerous targets, cannot sustain for individual celestial objects. V1935. Centauri's luminosity progression adheres to established patterns derived from decades of nova research. The initial ascent from invisibility to naked-eye visibility typically spans days to weeks. Peak luminosity can persist for anywhere from days to months, contingent upon the white dwarf's mass, the rate of accretion from its companion, and the elemental composition of the ejected material. The decline phase can extend over months or years, occasionally punctuated by secondary peaks, as distinct physical processes dictate the nova's energy output. Spectroscopy unveils the nova's chemical signatures. Early spectra typically exhibit broad emission lines from hydrogen, helium, and heavier elements moving at high velocities, indicative of the expanding ejecta. As the nova evolves, these lines narrow and shift as the ejected material cools and decelerates. Ultimately, forbidden lines emerge, transitions that can only occur in the extremely diffuse environments of expanding nova shells, where atoms might endure hours or days between collisions. The distances to V1935 Centauri and V79094 Sagittari remain somewhat imprecise, though they likely exceed several thousand light-years. This implies that the explosions we observed in December of 2025 actually transpired millennia ago, when human civilization was in its nascent stages of developing agriculture and permanent settlements. The light from these stellar detonations has traversed interstellar space for a duration longer than recorded human history, reaching Earth precisely during this remarkable week. Amateur astronomers can contribute significant observations using modest equipment. A digital single-lens reflex camera equipped with a telephoto lens can capture images of novae during their luminous phases. Visual observers utilizing binoculars or small telescopes can estimate magnitudes by comparing the nova to adjacent stars of known brightness. More sophisticated observers, equipped with CCD cameras and photometric filters, provide precision data that complements professional observations. The nomenclature system for nova designations reflects astronomical tradition and administrative procedures. V1935 Centauri acquired its permanent variable star designation as the 1935th officially catalogued variable within the constellation Centaurus. The prefix V denotes a variable star, an object whose luminosity fluctuates over time. This permanent designation supersedes provisional discovery names, which might incorporate the discoverer's surname, the date of discovery, or catalog numbers from various survey programs. The formation of dust represents one of the most captivating facets of nova evolution. Weeks to months following the initial eruption, some novae experience a drastic dimming as newly formed dust grains condense within the cooling ejecta. These dust dip events can diminish a nova's brightness by several magnitudes as microscopic particles absorb and scatter the nova's light. Eventually, the dust either dissipates or is disintegrated by the nova's ongoing radiation, allowing the underlying stellar remnant to reappear. The energy magnitudes involved in nova explosions vastly exceed human experience, yet remain modest in comparison to supernova. A typical nova releases energy equivalent to our sun's total output over approximately 10,000 years, sufficient to power human civilization for billions of years at current consumption rates. Nevertheless, this constitutes merely a minuscule fraction of the energy unleashed in supernova explosions, which can outshine entire galaxies for weeks or months. Recurrent novae complicate the straightforward depiction of single explosive events. Certain white dwarf systems undergo nova eruptions on comparatively predictable timescales, recurring every few decades for the most frequent offenders. These systems may experience dozens of nova explosions over astronomical epochs, gradually accreting enough material to approach the Chandrasekhar mass limit, at which point the white dwarf itself would detonate as a Type 1 supernova. Subsequent professional observations of both December novae continue across multiple wavelengths of electromagnetic radiation. Ground-based telescopes monitor optical brightness variations and spectroscopic evolution. Space-based observatories, including the Hubble Space Telescope, may capture high-resolution imagery of the expanding nova shells. Radio telescopes can detect synchrotron emission emanating from relativistic particles within the nova ejecta. The classification of V1935 Centauri and V79094 Sagittari as classical novae, rather than other forms of stellar explosions, hinges on spectroscopic evidence and patterns of brightness evolution. Dwarf novae, triggered by instabilities within accretion disks rather than thermonuclear explosions, typically display distinct spectral characteristics and less pronounced brightening amplitudes. Luminous red novae, potentially resulting from stellar mergers, exhibit differing color profiles and evolutionary timescales. Could either of these novae represent something more extraordinary than standard thermonuclear explosions? Current observational data supports classical nova interpretations, yet astronomy maintains a healthy skepticism regarding initial classifications. As more data accrues from multi-wavelength observations, the intricate physics may unveil subtleties that refine our comprehension of these specific detonations. The gamma-ray detection from V1935 Centauri places it within an emerging category of gamma-ray novae that challenge established models of nova physics. These high-energy emissions suggest particle acceleration processes operating more efficiently than previously believed possible within nova environments. The underlying physics may involve magnetic field reconnection, shock acceleration, or other mechanisms that bridge the gap between nova explosions and more energetic phenomena such as supernova remnants. As we tracked these stellar explosions across the electromagnetic spectrum, Earth's solid crust was concurrently preparing to demonstrate that our planet's interior could be every bit as dynamic as distant celestial bodies. Part 7. Anatomy of a Quake Cluster. Beneath Lake Maracaibo and the surrounding Zulia state of Venezuela lies one of South America's most tectonically intricate regions. The Caribbean plate grinds against the South American plate along a boundary zone encompassing numerous fault systems, including the Boconó Fault System, which runs northeast to southwest through the Venezuelan Andes, the Oca Ancon Fault trending east-west along the Caribbean coast, and the Santa Marta Fault extending into Colombia. These geological formations accumulate stress over decades, storing energy that must eventually be released through sudden slip events. The magnitude 6.2 earthquake that occurred at 2221 UTC on December 24th commenced as a rupture along one of these fault segments, approximately 7.8 kilometers beneath the surface. At this relatively shallow depth, seismic waves encountered less resistance during their journey to the surface, amplifying ground acceleration across a wide area. The initial rupture likely extended several kilometers along the fault plane, with sudden displacements measured in meters, releasing stress that had been building for years or decades. Seismic waves propagated outward from the rupture zone at approximately 6 kilometers per second through the surrounding rock. Primary waves, compressional disturbances that induce back-and-forth motion along their direction of travel, arrived first at seismograph stations throughout the region. Secondary waves followed, generating the side-to-side motion that typically inflicts the most damage upon structures. Surface waves, traveling more slowly but often carrying the most destructive energy, produced the rolling motions that eyewitnesses described as lasting for minutes in some locales. Merely 5.5 hours later, at 3:51 UTC on December 25th, a second major rupture struck virtually the same area. The magnitude 6.3 earthquake originated from a depth of 14 kilometers, deeper than its predecessor, but still shallow enough to generate intense surface shaking. This second event likely occurred on an adjacent fault segment, triggered by stress alterations induced by the initial rupture. The physics of stress transfer elucidates why earthquakes frequently manifest in clusters. When one fault segment abruptly slips, it modifies the stress field on nearby fault segments. Certain areas experience heightened stress, rendering them more susceptible to rupture in the near future. Other areas undergo stress relief, becoming temporarily less prone to generating earthquakes. The rupture on December 24th apparently imparted increased stress to the fault segment that failed 5.5 hours later. The difference in magnitude between the 6.2 and 6.3 earthquakes might appear insignificant, but the logarithmic nature of the magnitude scale signifies that the second event released approximately twice as much energy as the first. Combined, these twin ruptures produced energy equivalent to a single magnitude 6.4 to 6.5 earthquake, a substantial release ranking among the most significant globally. International seismological agencies reported slightly varying magnitudes for these events, reflecting the complexities inherent in earthquake measurement. The United States Geological Survey employs moment magnitude, calculated from the total energy liberated during the rupture. The European Mediterranean Seismological Center may utilize different magnitude scales based on surface wave amplitudes or body wave characteristics. These methodological divergences, coupled with updates as additional seismograph data becomes accessible, explain why headlines reported magnitude ranges from 6.1 to 6.3 for the initial event. The aftershock sequence followed patterns that seismologists have documented for decades. The magnitude 5.8 earthquake that occurred later on December 25th represents a typical large aftershock, smaller than the main shock but still significant enough to cause additional damage and concern. Omori's law, formulated in the early 1900s, describes how the frequency of aftershocks decays over time following major earthquakes. The largest aftershocks typically manifest within days of the main shock, with smaller events continuing for weeks, months, or even years. The human impact from these earthquakes extended across both Venezuela and Colombia. The relatively shallow depths amplified surface shaking, leading to evacuation directives for high-rise buildings in major cities. Social media platforms became inundated with videos of swinging light fixtures, rattling windows, and individuals evacuating structures as emergency protocols were activated throughout the region. While initial damage reports remained limited considering the earthquake's magnitudes, assessment teams spent days documenting both visible structural damage and potential long-term weakening of buildings and infrastructure. The regional geology helps explain the propensity for this area to generate such powerful earthquakes. The Maracaibo Basin formed through complex interactions between the Caribbean and South American plates, establishing a network of fault systems that accommodate ongoing tectonic motion. Lake Maracaibo itself is situated within a graben, a down-dropped block bounded by normal faults that continue to exhibit active deformation. The petroleum deposits that render this region economically vital formed within sedimentary basins created by the very tectonic processes that generate earthquakes. Depth measurements carry substantial uncertainty, particularly for earthquakes occurring in geologically complex regions. The 7.8-kilometer depth reported for the initial event and the 14-kilometer depth for the second represent best estimates derived from seismic wave arrival times at multiple monitoring stations. These depths place both earthquakes within the upper crust, where brittle fracture predominates over the ductile deformation that occurs at greater depths, where temperature and pressure escalate. The timing of these events prompted inquiries regarding potential triggers. Could solar activity, atmospheric pressure fluctuations, or other external factors influence earthquake occurrence? The scientific consensus, supported by the United States Geological Survey and international seismological organizations, maintains that no reliable correlation exists between these phenomena and earthquake initiation. Decades of statistical analysis have failed to establish predictive relationships between solar flares, coronal mass ejections, geomagnetic storms, and seismic events. However, some research has explored more subtle potential connections. Variations in atmospheric pressure can induce minute alterations in stress on fault systems, typically far smaller than the stress changes caused by Earth tides, which result from lunar and solar gravitational effects. While these influences remain detectable with sensitive instruments, they fall orders of magnitude below the stress thresholds required to trigger earthquakes on faults that are not already critically close to failure. The Global Centroid Moment Tensor Database provides detailed analyses of fault orientations, slip directions, and rupture mechanisms for both Venezuelan earthquakes. These beach ball diagrams illustrate which fault planes actually moved and in which directions, providing information that assists seismologists in understanding regional stress fields and predicting which fault segments might face elevated risk in the future. Statistical seismology offers the only reliably predictive approach to earthquake forecasting currently available. Following major earthquakes, such as those in Venezuela, the probability of additional large events in the same vicinity temporarily increases due to aftershock activity and stress transfer effects. However, this heightened probability typically persists for weeks to months and cannot pinpoint the exact timing or location of future earthquakes. Building codes and emergency preparedness systems face continuous scrutiny in seismically active areas like Zulia State. The comparatively moderate damage reports following the magnitude 6.2 and 6.3 earthquakes likely reflect both fortunate circumstances and ongoing improvements in construction standards. Modern seismic building codes mandate that structures withstand strong ground motion, although older buildings may remain vulnerable to damage or collapse. Could larger earthquakes occur in the same region? The geological setting certainly accommodates more powerful events. The fault systems surrounding Lake Maracaibo have historically generated magnitude 7 earthquakes, and regional tectonics suggest that such events will continue to occur sporadically over geological time. Nevertheless, seismologists cannot predict whether days, years, or decades might elapse before the next significant rupture. The Venezuelan earthquake sequence exemplifies how solid Earth processes can produce dramatic energy releases on human timescales while adhering to physical laws that operate over geological time. Stress accumulates gradually as tectonic plates slide past each other at rates measured in centimeters per year. When accumulated stress surpasses the rock's strength, sudden failure releases decades or centuries of stored energy in seconds to minutes of violent shaking. As aftershocks continued to rattle the Caribbean-South American plate boundary, our focus shifted to the space environment, where another form of energy release was unfolding on scales that dwarf terrestrial earthquakes. Part 8. The Sun at Maximum. Solar Cycle. 25 reached its peak activity during 2024 and 2025, transforming our typically placid star into a restless giant capable of hurling billion-ton plasma clouds across the solar system. On December 24th and 25th, stellar explosions illuminated southern skies while earthquakes vibrated Venezuelan bedrock. Solar activity indices depicted a sun operating near its zenith of fury. The 10.7 centimeter radio flux, a crucial indicator of solar activity levels, hovered around 180 to 190 solar flux units in late December. This measurement, recorded daily by radio telescopes, correlates strongly with the number and intensity of active regions on the sun's surface. Values exceeding 150 typically signify elevated solar activity, while readings above 200 suggest very active conditions capable of generating significant space weather events. Sunspots themselves tell a story of magnetic chaos unfolding in the sun's photosphere. These dark regions, often larger than Earth, form where potent magnetic field lines pierce the solar surface and impede normal convective heat transport. The magnetic field strength within sunspot cores can surpass 3,000 Gauss, approximately 6,000 times stronger than Earth's surface magnetic field. More sunspots generally equate to greater opportunities for magnetic field lines to tangle, reconnect, and explosively release energy in the form of solar flares and coronal mass ejections. However, raw sunspot counts merely hint at the complexity of solar maximum conditions. The sun's magnetic field during peak activity resembles a tangled, knotted mess, rather than the relatively straightforward dipole field that dominates during solar minimum. Active regions, clusters of sunspots interconnected by magnetic field loops, can persist for weeks or months, rotating across the solar disk and occasionally producing spectacular eruptions observable by spacecraft throughout the inner solar system. Coronal mass ejections represent the most dramatic manifestation of solar maximum physics. These events commence when magnetic field lines in the sun's corona become so contorted and stressed that they abruptly snap and reconnect, converting magnetic energy into the kinetic energy of charged particles. This process launches billion-ton clouds of plasma into space at speeds ranging from 250 kilometers per second for slow events to over 3,000 kilometers per second for the most rapid eruptions. The NOAA Space Weather Prediction Center utilizes the WSA-NL model to monitor these solar eruptions, a system that maps the propagation of coronal mass ejections through the heliosphere. This model divides the vastness of space into a three-dimensional grid, extending from the sun far beyond Earth's orbital path. It calculates how solar wind velocity and other factors evolve as plasma clouds traverse the solar system. While ENLIL proves effective at forecasting general arrival times and the intensity of these events, it cannot fully account for every nuance of a CME's structure and behavior. The period around the autumnal equinox traditionally intensifies space weather phenomena due to a process referred to as the Russell-McLaren effect. This geometric interaction stems from the alignment of Earth's magnetic field in relation to the interplanetary magnetic field carried by the solar wind. During equinox periods, this alignment facilitates magnetic reconnection between the solar wind's magnetic fields and Earth's magnetosphere, frequently triggering significant geomagnetic storms, even from relatively minor solar disturbances. The ramifications of space weather extend far beyond the visually striking aurora displays that capture public imagination. Geomagnetic storms can severely disrupt high-frequency radio communications essential for aviation and maritime operations, compel satellite operators to adjust spacecraft trajectories due to increased atmospheric drag, and in severe instances, jeopardize the stability of power grids by inducing electrical currents. NOAA maintains standardized scales for geomagnetic storms, designated the G scale, for solar radiation storms, the S scale, and for radio blackouts, the R scale, assisting various industries in their preparedness and response to space weather impacts. The interplay between coronal mass ejections and comets serves as an invaluable natural laboratory for investigating plasma physics under conditions unattainable on Earth. Ion tails form when the solar wind strips electrons from gas molecules within a comet's coma, generating charged particles that subsequently follow magnetic field lines directly away from the sun. These tails can stretch for millions of kilometers through space, offering tangible evidence of the unseen magnetic forces at work between our star and smaller celestial bodies within the solar system. When a CME intersects with a comet, the encounter can be both dramatic and visually spectacular. The European Space Agency's stereo satellites documented precisely such an event in the year 2007, when a coronal mass ejection completely severed the ion tail of Comet Encke through magnetic reconnection processes. The detached tail drifted away from the comet over several hours, while a new tail began to form from fresh material, vividly illustrating the dynamic nature of space weather interactions. Solar maximum conditions during 2025 provided a particularly active environment for 3I Atlas as it journeyed toward the inner solar system. Unlike preceding interstellar visitors that encountered our Sun during less active phases of the solar cycle, this object experienced space weather effects at or near their peak intensity. The confluence of increased CME frequency and the visitor's trajectory through the ecliptic plane, where most solar system activity is concentrated, maximized the likelihood of significant interactions. The physics governing CME propagation involves intricate magnetohydrodynamic processes operating across scales ranging from the motion of individual particles to structures larger than planetary orbits. Rapid CMEs can overtake slower solar wind streams, creating compression zones and shock fronts that accelerate particles to high energies. Multiple CMEs can collide, merging into more substantial, powerful disturbances, or generating complex magnetic field configurations that amplify particle acceleration and magnetic reconnection. Professional space weather forecasters meticulously monitor a multitude of data streams to track solar activity and anticipate potential impacts on Earth. The Solar Dynamics Observatory continuously provides high-resolution imagery of the Sun's surface and corona across various wavelengths of extreme ultraviolet light. The Solar and Heliospheric Observatory observes for CMEs erupting from the Sun's far side. The Advanced Composition Explorer, positioned between Earth and the Sun, offers advanced notification of incoming solar wind disturbances. Amateur radio operators function as an informal, global network for observing space weather effects on our planet. High-frequency radio propagation undergoes significant alterations during geomagnetic storms, occasionally enhancing long-distance communication through increased ionospheric reflection, while diminishing it at other times due to heightened absorption and scattering. These real-time observations supplement the formal measurements obtained from professional monitoring stations. The current solar maximum appears to be exhibiting a pattern with two distinct peaks, a phenomenon observed in some prior cycles, with an initial surge of activity in 2024, followed by sustained high activity through 2025. This prolonged maximum phase signifies that heightened space weather risks may persist longer than the typical 11-year cycles, maintaining conditions conducive to dramatic solar-terrestrial interactions well into 2026. Aurora photography and observation have surged in popularity during the current solar maximum, with social media platforms awash with stunning images of green, red, and purple lights dancing across polar and subpolar skies. These captivating displays are the result of charged particles from solar storms interacting with Earth's upper atmosphere, energizing oxygen and nitrogen atoms that then emit characteristic colors as they return to their ground states. The solar wind itself carries embedded magnetic fields that originate in the Sun's corona and extend throughout the solar system as outward flowing plasma. These interplanetary magnetic field lines form a vast network connecting planets, comets, and spacecraft in an intricate web of electromagnetic influence that extends to the heliopause, the boundary where the pressure of the solar wind is balanced by the pressure of the interstellar medium, located approximately 100 times farther from the Sun than Earth. As we tracked solar storms moving through the inner heliosphere in late December of 2025, one particular celestial body commanded the attention of space weather forecasters and astronomy enthusiasts alike. An interstellar visitor traversing this cosmic storm system on its approach to its initial encounter with another world. Part 9. 3 Atlas on approach. In the early morning hours of July 1st, 2025, the Asteroid Terrestrial Impact Last Alert System Telescope Array detected an extraordinary object moving against the backdrop of stars. Initial observations suggested a faint, comet-like entity, but subsequent orbital calculations swiftly revealed its true nature. 3 Atlas, only the third confirmed interstellar visitor in recorded human history, following the enigmatic Oumuamua in 2017 and Comet Borisov in 2019. Its designation encapsulates its discovery and significance. The prefix 3I signifies that it is the third interstellar object catalogued by the International Astronomical Union, while Atlas honors the telescope system that first spotted this celestial wanderer. In contrast to its predecessors, 3I Atlas arrived during a uniquely advantageous observational window, sufficiently bright for detailed study, following a trajectory that keeps it near the ecliptic plane where most solar system activity is concentrated, and approaching during a solar maximum period that offers unparalleled opportunities to investigate how our star influences interstellar matter. The visitor's orbital characteristics underscore its extraterrestrial origins. Its trajectory exhibits a hyperbolic shape with an eccentricity significantly exceeding 1, indicating it possesses more than ample velocity to overcome the Sun's gravitational pull. The orbital inclination of approximately 175 degrees signifies that 3 Atlas travels in a retrograde direction relative to the planets, moving in opposition to the typical flow of solar system traffic. Current models suggest the object's dimensions range from several hundred meters to potentially 15 kilometers in diameter. Although these size estimates carry considerable uncertainty, direct imaging remains beyond the capabilities of even the most powerful ground-based telescopes. The visitor appears as little more than a fuzzy, star-like point of light surrounded by a faint coma of gas and dust. Size estimations are contingent upon assumptions regarding the object's reflectivity, composition, and activity level, all unknown variables for an object that originated around a different star. October 3, 2025, marks a crucial milestone in the study of interstellar visitors. 3I Atlas will pass within 0.19 astronomical units of Mars, approximately 28 to 30 million kilometers from the red planet. This close proximity presents unprecedented opportunities for detailed observations utilizing Mars orbital missions, including ESA's ExoMars Trace Gas Orbiter, NASA's Mars Reconnaissance Orbiter, and other spacecraft positioned to observe the visitor from an exceptionally advantageous vantage point. Harvard astronomer Avi Loeb described the Mars encounter as a blind date between an interstellar visitor and our neighboring world. The Mars Reconnaissance Orbiter's high-rise camera, capable of resolving features as small as 30 centimeters on the Martian surface, is expected to achieve pixel scales of roughly 30 kilometers when directed toward 3I Atlas during its closest approach. While this resolution will not reveal surface details of the visitor's nucleus, it may differentiate between a compact central condensation and a more diffuse coma structure. The scientific value of these observations extends beyond mere imaging. Spectrographic measurements during the Mars flyby could unveil the chemical composition of gas escaping from the visitor's nucleus as solar heating liberates ancient volatile compounds. Expected spectral lines include CN, cyanogen, CO, carbon monoxide, and CO2, carbon dioxide, molecules that would provide direct evidence of the visitor's chemical makeup and offer clues about the conditions in its birth stellar system. Amateur astronomers globally have contributed vital observations of 3I Atlas throughout its approach. Early reports indicated a faster-than-anticipated brightening as the object drew nearer to the Sun. Although these preliminary light curves necessitate careful calibration and verification, the visitor's southern sky position favors observers in the southern hemisphere, though observers in the northern hemisphere can track it during the early morning hours when it rises above their southern horizon. Professional observatories are coordinating ongoing observation campaigns through organizations such as the American Astronomical Society and the Minor Planet Center. These collaborative efforts aim to characterize variations in brightness, changes in tail morphology, and spectroscopic evolution. As 3i Atlas responds to increasing solar heating during its inbound trajectory, its path through the inner solar system offers numerous observation opportunities extending into early 2026. Following the Mars flyby on October 3rd, 3 Atlas continues its journey toward perihelion, its closest point to the Sun, on October 29th, at an approximate distance of 1.36 to 1.4 astronomical units from the Sun. This distance places it outside Earth's orbit, but well within the observational range of ground-based telescopes and space-based observatories. December 19th marks 3 Atlas's closest approach to Earth at roughly 1.8 astronomical units, approximately 270 million kilometers. For comparative context, this distance is closer than Mars at its most distant point from Earth, providing exceptional viewing conditions for both professional observatories and amateur astronomers equipped with modest telescopes throughout late 2025 and early 2026. The visitor's behavior near perihelion may reveal whether it conforms to typical cometary evolutionary patterns or exhibits unique characteristics reflective of its interstellar origins. Solar heating could liberate volatile compounds that have remained frozen for millions of years during the object's long journey through interstellar space. The consequent outgassing might lead to dramatic increases in brightness, tail development, or other phenomena that distinguish interstellar visitors from comets within our solar system. Tail morphology presents one of the most captivating aspects of the 3i Atlas observations. Professional imagery reveals anti-sunward ion features consistent with typical cometary behavior, while some amateur observers report forward-facing dust structures that appear to deviate from established cometary physics. These apparent discrepancies likely stem from the differing physical processes governing dust and ion tail formation, rather than from exotic phenomena. Dust tails are formed by radiation pressure, the gentle yet persistent force exerted by sunlight on microscopic particles ejected from the comet's nucleus. These particles follow curved trajectories as they respond to both solar radiation pressure and gravitational attraction, creating the elegant, curved tails commonly seen in cometary photographs. Dust tails can appear to point in various directions depending on the viewing geometry and the observer's position relative to the comet's orbital plane. Ion tails, conversely, are formed through entirely distinct physical mechanisms. The solar wind strips electrons from gas molecules in the comet's coma, creating charged particles that become electromagnetically bound to magnetic field lines embedded within the solar wind. These charged particles stream directly away from the Sun along these magnetic field lines, forming the narrow, straight tails that alter their direction as the orientation of the solar wind's magnetic field fluctuates. The uncertainties surrounding the size and composition of 3 Atlas highlight the fundamental challenges inherent in studying objects at interplanetary distances. Even the most powerful telescopes are incapable of resolving surface details of objects smaller than major asteroids at ranges exceeding several astronomical units. Size estimations rely on measurements of brightness, assumptions about surface reflectivity, and models depicting how much light the object scatters toward Earth. Some media reports have speculated that 3i Atlas could measure up to 15 meters in diameter. However, these estimates should be approached with caution until further substantiated by thermophysical modeling that integrates brightness measurements with infrared observations of thermal emission. The object's activity level, the rate at which it releases gas and dust relative to its size, also influences its apparent brightness in ways that complicate size determinations. The visitor's approach coincides with another spectacular celestial event that promises to make October of 2025 a month to remember for skywatchers worldwide. But first, we must understand what transpires when our sun interacts with objects that have spent eons journeying between the stars. Part A is coming. While 3I Atlas garners considerable attention as an interstellar visitor, October of 2025 holds the promise of a second celestial spectacle that could potentially eclipse it. Comet C 2025 R2, discovered in SOHO SWAN data by amateur astronomer Vladimir Bezus in December 11th and 12th, is rapidly approaching its closest encounter with Earth on October 20th and 21st, with the potential to reach naked-eye visibility during the same weeks that 3 Atlas is performing its Mars flyby. The story of its discovery itself underscores the power of citizen science in contemporary astronomy. The Solar and Heliospheric Observatory, SOHO, continuously monitors the Sun's corona and the surrounding space environment. Its SWAN instrument, the Solar Wind Anisotropies instrument, maps hydrogen emissions throughout the heliosphere, occasionally detecting comets as they brighten and begin to outgaze while approaching the inner solar system. Vladimir Bezus, while examining publicly accessible SWAN data, noticed a brightening object that did not correspond to any known comet or asteroid. His meticulous analysis of multiple images confirmed the object's cometary nature and provided preliminary orbital calculations, suggesting it was a long-period comet, making its first recorded approach to the inner solar system in recorded human history. Comet Swan reached perihelion, its closest point to the Sun, on December 12th, mere days after its discovery. This timing accounts for the rapid brightening that initially captured Bezos's attention. Comets typically exhibit their most dramatic brightening as they approach perihelion, when increasing solar heating releases volatile compounds from their nuclei, forming the characteristic coma and tail structures that render them visible from Earth. The orbital geometry favors October observations from both hemispheres, although observers in the southern hemisphere initially enjoyed superior viewing conditions. As October progresses, the comet's position relative to Earth and the Sun improves for northern hemisphere observers, potentially offering excellent viewing opportunities for the largest segment of amateur astronomers and casual sky watchers. Current brightness predictions indicate that Comet Swan could reach a magnitude of 4 to 6 during its closest approach to Earth, bright enough for naked-eye visibility under dark skies, although binoculars or small telescopes would reveal significantly more detail of its coma and tail structure. These brightness estimates carry substantial uncertainty, as cometary behavior remains notoriously unpredictable, particularly for new comets making their first recorded journey into the inner solar system. The timing creates an ideal confluence of celestial events during late October of 2025. The new moon phase, occurring around October 20th and 21st, eliminates lunar interference, which often obscures faint celestial objects. The annual Orionid meteor shower reaches its peak activity during these same nights, caused by debris from Comet Halley intersecting Earth's orbit. Skywatchers could potentially observe a bright comet, multiple meteors per hour, and the ongoing evolution of 3I Atlas, all during the same optimal viewing sessions. Comet Swan's classification as a long-period solar system comet stands in stark contrast to the interstellar origins of 3I Atlas. While both objects likely contain similar volatile compounds, water ice, carbon monoxide, carbon dioxide, and various organic molecules, they originated in entirely different environments. Comet Swan condensed from material in the outer reaches of our own solar system approximately 4 billion years ago, potentially spending the majority of its existence in the distant Oort cloud before a gravitational perturbation sent it sunward. The scientific questions posed by each object are accordingly distinct. 3 Atlas offers insights into stellar system formation processes, interstellar chemistry, and the effects of cosmic radiation on materials during million-year journeys between stars. Comet Swan provides information regarding conditions in the early solar system, the composition and structure of the Oort cloud, and how solar heating affects pristine cometary materials, making their first close approach to the Sun. Photographic opportunities abound for both professional and amateur astronomers during October's dual cometary spectacle. Wide-field cameras can capture both objects within the same frame, documenting their relative positions, brightness, and tail structures for comparative analysis. Time-lapse photography could effectively illustrate changes in coma morphology, tail orientation, and overall brightness. As solar wind conditions fluctuate and the object's distances from Earth and the Sun change daily, the inherent unpredictability of cometary brightness evolution injects excitement and uncertainty into October's viewing prospects. Some comets significantly exceed brightness predictions, developing spectacular tails and reaching magnitudes that render them unmistakable naked-eye objects, even from light-polluted urban areas. Others prove disappointing, failing to brighten as anticipated or fragmenting under the stress of solar heating in ways that diminish their visual impact. Comet Swan's limited observational history makes reliable predictions particularly challenging. Unlike periodic comets that return regularly, allowing astronomers to study their behavioral patterns over multiple apparitions, new long-period comets like Swan offer no historical precedent for their brightness evolution, outgassing rates, or structural stability under solar heating. The potential for dramatic tail development adds significant visual appeal to October's cometary viewing opportunities. Both dust and ion tails could emerge as prominent features, especially given the continued elevated solar wind activity during solar maximum conditions. Celestial events, such as coronal mass ejections detaching ion tails from comet nuclei, could soon be observable in real time through telescopic viewing. This would grant us uncommon insights into the dynamics of space weather as it unfolds. Enthusiast astronomers utilize diverse strategies to monitor shifts in luminosity and the evolving shape of comets. Visual estimations of their brightness, compared against nearby stars of known magnitude, yield valuable data that permanent observatories are unable to gather continuously. Photographic techniques employing digital cameras and charge-coupled device systems provide more accurate measurements while simultaneously documenting alterations in the structure of the coma and tail features. The prospect of Earth potentially encountering remnants from Comet Swan injects an element of speculation into observations scheduled for October. Should our planet's trajectory intersect the dust trail left by the comet from its past journeys through the inner solar system, we might witness a modest meteor shower as these particles ingress Earth's atmosphere. However, such occurrences remain highly unpredictable for recently identified comets lacking well-established debris trails. Spectroscopic analysis of both comets during October could unveil chemical parallels and divergences, shedding light on their origins. Professional observatories equipped with spectrographs can detect spectral lines from specific molecules like cyanide, diatomic carbon, atomic oxygen, and amidogen, indicating which volatile compounds are vaporizing from each nucleus due to solar heating. These chemical signatures offer direct evidence of composition and formation conditions. The logistical requirements for observing October's twin comet spectacle favor observers situated under dark skies with unobstructed horizons. The pervasive light pollution in urban areas severely diminishes the visibility of faint celestial objects, making rural or wilderness locations essential for optimal comet viewing. Weather patterns during the latter part of October exhibit considerable variability depending on the geographic location, necessitating adaptable planning for successful observations. For casual observers, binoculars often prove more effective for comet viewing than telescopes. Their wide field of view presents the entire comet, nucleus, coma, and tail, in context rather than magnifying small sections, which can detract from the overall visual impact. 7 by 50 or 10 by 50 binoculars represent ideal choices, offering sufficient light gathering capability to reveal faint details while maintaining comfortable viewing angles. The simultaneous appearance of two bright comets during October 2025 presents unparalleled opportunities for comparative studies. Viewing them side by side could highlight disparities in coma coloration, tail orientation, and overall form, reflecting their distinct origins and evolutionary paths. Time-lapse photography spanning several nights could capture how each object reacts to changing solar wind conditions and viewing geometry. Professional observatories globally have organized collaborative observation campaigns for both celestial bodies, ensuring comprehensive monitoring across multiple segments of the electromagnetic spectrum. The Hubble Space Telescope may capture high-resolution imagery capable of resolving structural intricacies beyond the reach of ground-based observatories. Radio telescopes could detect molecular emission lines, revealing the chemical makeup and temperature distribution within the expanding coma regions. Safety considerations for observing comets are minimal when contrasted with viewing solar or lunar eclipses. Comets pose no direct hazard to observers and necessitate no specialized filters or protective gear beyond standard precautions for nighttime outdoor excursions.